As more and more software and devices are connected to the internet, and adversaries become better at breaking into systems, software needs to become more secure. Fuzzing is an automated approach for testing software that involves 3 key steps: input generation, program execution, and monitoring. By repeating this process potentially many millions of times, fuzzers have found reliability, correctness, and security issues in a wide range of software. This software has included web browsers, operating systems, and IoT devices. In fact, fuzzing has become so critical to the security of modern software that large companies require fuzzing to be deeply integrated as part of their development process. In my research, I focus on emulation-based fuzzing. This approach makes use of an emulator to take care of the execution and monitoring of the program. Because execution occurs inside of an emulator, it is easily scalable, we can add instrumentation without source code, and we can test software that was originally designed for different hardware, such as in firmware and IoT devices. Existing emulation-based fuzzers build on platforms designed for general-purpose emulation, not for fuzzing. For each supported architecture, there is a manually written translator. This translator takes the original program code and, using a just-in-time compiler, converts it into a form that can be executed in a manner suitable for fuzzing. Instrumentation and monitoring are either added as part of the translation process or the just-in-time compilation step. My research looks at improving emulation-based fuzzing by building a new emulation platform that deeply integrates fuzzing as part of its design. Instead of writing translators manually, they are instead generated from a processor specification language. This greatly reduces the work needed to support new architectures. Each generated translator takes the original machine code and converts it into an architecture-independent intermediate language. Once in this form, the fuzzer can perform optimizations, implement monitoring and instrumentation, all in an architecture-independent manner. This framework provides the potential to improve runtime performance by allowing the development of optimizations specific to fuzzing, and therefore allowing more bugs to be found and for them to be found faster. It also makes it significantly easier to add instrumentation in an architecture-agnostic manner. This allows new and more sophisticated fuzzing techniques, perhaps originally developed for general-purpose fuzzing, to be also used in finding new vulnerabilities in firmware and IoT devices. Finally, since emulation and fuzzing is deeply integrated together, it makes the system significantly easier to use. This allows fuzzing to be used by more than just specialized practitioners, resulting in better, more secure software as fuzzing increases in use.